Hi. I'm sorry for being late. There seemed that there was a problem with last lecture. Somehow it did not get recorded and posted, and so I was talking to them to make sure it wouldn't happen again today. But they don't seem to know what the issue is, so hopefully it will be recorded and posted. This is an automated system, and I have no participation in it, and somehow it was not posted from last time. So I put this on the course webpage and do refer to it for next class, which is the midterm. And so if your family name starts with anything from A to K, then you are in the room here. If your family name starts between L and T, you are in the Strathcona Dentistry Building, room M1. And if your family name is between U and Z, it's in Burnside Hall, 1B39. It was posted 1B45 before, but ignore that 45. It was switched to 39. And so this is the 3 rooms we've been allocated to run the midterm. Okay, and of course, if you are supposed to do that in a different room, you know, if you are working with students with disabilities, you know where to go. It doesn't concern you, but otherwise, this is where you should all go. Okay, and it will be difficult to accommodate people who go to the wrong place, so please take good note of it and make sure that you all go to the right place. Also, I was asked a few times what material is going to be on the midterm. Well, it's up to lecture 10. Now, in a sense, this is fortunate because the last one was 11 and is the one who's missing on the recording right now. And so it's good because you don't have to know this material for the midterm. But I'll just keep checking with them as what's going on and what happened for the 11th lecture. There were some questions about the midterm format and so on, so please, whoever had questions, please go ahead and ask me now. Yeah? Okay, so, well, okay, I'm going to repeat. I mean, the assignment submission has to be done electronically, so if you write it on paper, please scan it, make it a PDF, and submit it in. So this way, the TAs can get different questions separated from your file, and it's much easier than from paper. So all submissions should be done electronically. And your question is? Yes, well, unless you wrote everything in text format, but that would be surprising to me that you can manage to do everything just with text format. But PDF is what we expect, yes. Yes? Sorry? Well, I wish I could definitely answer yes or no right now, but I have not written the midterm yet. So the answer is it's still possible, but if it were the case, it would be pretty minimal. I mean, the purpose of this course is not really about programming, and you have done some programming exercise on the first assignment, but programming is the tool, and it's the other stuff that we're really learning. So don't expect much more than a few lines of codes that maybe I'll write in Java because it's easier, and then you have to understand that. Or maybe I'll ask you an algorithm, and there's a few notions like linked lists and so on that you may want to use a Java-style way of writing it. But I don't plan to have a question which is program this. I mean, definitely not. I mean, look, there are various other professors in the school that have taught 250 in the recent years, and there are several web pages available to other people with Comp 250. And if they still have midterms on their web pages, of course, I encourage you to go there. But most people don't like to keep their midterms and finals around web pages forever because it restricts future questions. And so I'm not going to go around and query. I mean, I haven't taught it since 2004. The one version I'm giving you is the last one that I prepared. Other people probably prepared exams, but I'm not going to go around and try to sample more midterms and post them. No. Yes? Sorry? It's already there. Yeah. Yes. Okay, so the midterm is definitely going to be multiple choice. Okay, so I take advantage of the fact that I volunteer into receiving 360 exam books for the midterm. I'm not volunteering to do that on the final. So expect the final to be much more in the multiple choice environment, and expect that for the final. Okay, because on the final, I'm not going to run a 3-hour exam where you turn in 360 booklets for exams. No way. Okay, so the midterm is shorter, you have much less time, and so I will check things that I will not be able to check on the final. So for instance, do expect a small but an induction proof of some sort. Okay, there will be one, and it will be reasonable. It's not going to be something very complicated, but I expect all of you to be able to answer that and give me that. Okay, but it's not going to be multiple choice format. It's definitely going to be questions that you need some amount of space to answer on the midterm. And the final is going to be completely different. Yeah. Okay. So as I said last time, we are going to cover today what is called the master theorem, which comes from, well, many books, but it's particularly thorough in that reference to which you have access on the course webpage. You can actually go into the book. If you're from a McGill site, you can actually see the book, and so you can look at that chapter if you like. And so what I told you last time is the context in which the master theorem is going to be applied. And this is situations that we call divide and conquer recurrences. And I'll tell you after this discussion of the theorem itself, I'll say a bit more about divide and conquer, but that's a pretty straightforward idea. We will encounter many of these recurrences, typically for running times that have the form that the running time for inputs of size n is related to the running time of several. Well, when a is 1, it's not several, but when a is greater than 1, it will be several. And typically, this a is an integer. It's how many sub-instances of the problem are we solving recursively. And the size of the sub-instances that we're solving are of size n over b. So b is the divider that reduces the size of the input. And the principle of divide and conquer is to solve the input of size n by solving a inputs of size n over b and recombining them in a solution for n. And the amount of time required to break down and recombine the answer is f of n. Now, the power of the master theorem is to give us the solution to such recurrences in many, many cases. It's not absolute in the sense that it doesn't allow us to solve all such recurrences, but we're going to see very large families that we can actually solve. And the solution to such recurrences depend completely on these three parameters. They depend entirely on the constant A, the constant B, and the function f of n. And it's the relation between these three that really establish what's going to be the solution to the recurrence T of n. So what we call the master theorem is essentially the fact that we find the solution to this recurrence exactly by comparing two functions. So one function is given by f of n. It's the amount of work which is necessary to split and recombine. And we compare that to a function that is constructed by a and b, and the function is n power log base b of a. So it's definitely the relation between E and B, A and B given by this log B of A, which establishes what will be the solution to T of n when compared with f of n. And so depending on which of the two here is greater in big O notation, so depending on which of these two functions is more important, either this will dominate and then the total solution to T of n is going to look like this, or this f of n is going to dominate this other part, and then the solution is going to look like f of n, or they're equal, and when they're equal, well, they both could be solutions, but an extra log n is going to pop in when they are equal. Now let me give you at least an intuitive explanation as how this is going to happen. Why is it that if I start with a recurrence of this type, I will end up comparing the function f of n with the function n power log b of a. Now, I'm going to draw a tree here and count at each level what is the cost of that level if I expand this in a telescopic or forward substitution manner. So I substitute what is T of n? Well, T of n will cost f of n to recombine. So on that level, I'm going to write f of n because that's necessary to compute T of n. And it's going to cost me a of, at the next level, a times T of n over b. So in this example, I'm using a equal 3 because I'm splitting 3 ways. But for a equal 25, then there would be 25 elements on this level. But so in general, the next level will be made of a times T of n over b. And I now want to find out how much are those going to cost extra to the level for T of n. So at the level for T of n, I have this much, and I'm going to have whatever comes out of these, a T of n over b. Now, to simplify everything, we assume that n is a power of b, in the sense that whenever I divide by b, I always get an integer. Because otherwise we have to involve floors and ceilings and things get more messy. So just assume, for simplicity, that the number n we're talking about is actually a power of b. So we can deal with integers everywhere. Now at that level, we have a times T of n over b. And if I expand T of n over b, I'm going to get a T of n over b squared plus f of n over b. So if I substitute the n from this expression with n over b, then I get at of n over b squared, and I get f of n over b. So that means that there will be a cost at this level of a f of n over b for these f of n parts of that level. And there will be a of them because there's one for each of those recursions. And now there will be extra, which corresponds to this, splitting down into a t of n over b squared, and so on. So what's going on at each level is that at the top level, I'm going to have a cost which is f of n. At the next level, I'm going to get a cost which is a f of n over b for those splitting a times on instances of size n over b. And at the next level, basically the same thing is going to happen again. So the next level, there will be a squares of those identical subproblems, and they will each create an f of n over b square amount, and there will be a square of them. So the f of n part, when I count it for each of these a square possibilities, there will be a square of them, and each one of them will contribute f of n over b squared. And so this is exactly what's going on at each level. At each level, it's splitting by a multiple of a more subinstances, and the subinstances that we create are a factor of b smaller. So after k repetitions of this, the cost is going to be a power k f of n over b to the k. So this is what we have basically at each level. And this is going to keep repeating until we get at the bottom of the tree. And let's say we reach the bottom of the tree with with n equal 2 when we divide and divide and divide. And when we get there, we're going to get a constant, which is the value of t of 2, which appears everywhere. And how many of them will I have? Well, I will have as many as a to the power, the number of levels that we took from the top to the bottom. So this entire expansion of t of n lead us at the very bottom that we have a constant t of 2 multiplied by a power log b of n, because the total number of levels is going to be log b of n. Because if I start with one element of size n, and then the next level is n over b, and then the next level is n over b squared, well, after n over b to the log b of n, this b and log b are going to cancel out. It's going to give me n, and I'll be down at 1 or at 2. So what is important here is that the behavior of this is the same at all levels, but it will stop after log b n levels. Yes? Okay, so the total cost is the sum that we have up here. The total cost is the sum of all these levels. Okay? So the total cost for the entire expansion of this recurrence will be the sum of all these levels. Now, before I complete the explanation, I have to point out one important fact, which is very easy but very important. It's the fact that if I have an expression like a to the log b of n, I can rewrite it as any base b to the log b of n times log b of a. because b to the log b of a is a, and so a to the log b of n is a to the log b of a. So I'm not changing the value by replacing a by b to the log b of a. Now this may seem surprising, but now if I do b to the log b of n, I'm going to get n to the log b of a. Which means that these two expressions, when I have a base power, a log of something, I can always switch the base and that thing here. So if I have a to the log b of n, that's the same as n to the log b of a. Now this n to the log b of a is the one thing we're going to consider to compare with f of n. And it comes from the fact that the last level here has an a to the log b of n in it. And if we kept it in that form, you'd be always asking yourself, what does a to the log b of n really mean? How big is my a to the log b of n, right? But in reality, this is just a polynomial in n. This is n to some power, to some exponent, which is fixed by a and b. You just look at a and b, you compute this log base e of a, and it tells you what is the power of n that is. And in the end, what happens is that the total cost for all these levels is going to be this sum. The sum corresponding to T of n is the sum of all the ak f of n over b to the k. Now, if f of n is much greater asymptotically than the last n to the log b of a, then this sum is going to be dominated by f of n. Which means that if f of n is significantly greater than that last term here, then the whole sum is going to behave like f of n. On the opposite, if n to the log b of a is much greater than f of n, then this entire sum is going to behave like n to the log b of a. So it's either behaving like the top term or the bottom term, if one is dominating the other substantially. But if it's not, if they're all pretty much the same, if f of n and n to the log b of a are pretty much the same, then all these levels are going to be worth pretty much the same. And then the sum of all of them is going to be the same thing times log n, because there are log n levels. So basically what this explanation tells us is that this summation is going to behave in essentially three ways. Either the function is going to be pretty much like the first level and everything else doesn't really matter, or it's going to behave like the last level and everything else doesn't much matter, or all the levels are pretty much the same, and then we multiply the whole thing by log n because there are log n levels. Okay, so these are the three cases that the master method is going to tell us. It's going to tell us there are three solutions essentially to this type of recurrences, and they correspond to having all the weight at the top, all the weight at the bottom, or equal weight everywhere. Okay, so this results in the three cases of the master method. The first case is if f of n is not only big O of log b of a, of n to the log b of a, but it's actually big O of something, of some exponent smaller than log b of a. So if the relation between f of n and log b of a is so that f is big O of log L for some L less than log b of a, then it's log b of a which is dominant in this entire relation. Because what this is saying is that really f of n is in big O of log b of a, but n to the log b of a is not big O of f of n. So a different way of interpreting case one is that f of n is big O of log n to the log b of a, but the opposite is not true. Well, when that happens, then f of n is sort of negligible in the whole story, and what counts is n to the log b of a, and that dominates the running time. So if you look at it, when that happens, it's as if f of n did not exist. If you take the same recurrence and you remove f of n, you're going to get the same solution. Okay, so if f of n is not big enough compared to n to the log b of a, it's really as if f of n did not exist, and we really don't care about it. The solution is going to be that t of n is n to the log b of a. The second case is the more complicated of all three cases. It's the case where f is exactly the same in theta notation as n to the log b of a, potentially multiplied by some log. I'll show you examples of each of those, so let me get back to this one in more detail with the example. But the middle case, case 2, is essentially the case where f of n and n to the log b of a are of the same magnitude. And the third case is the case where f of n is the dominating part. F of n is omega of n to the L for some L greater than log b of a. But the third case has a little glitch to it. To actually prove what it does, we need an extra constraint. Fortunately, that extra constraint is going to be true pretty much for all the algorithms we see. So it's not a big deal in applying it. However, to mathematically prove that the solution to the third case is this, we need this extra condition. And the extra condition is a so-called linearity condition, that we need f to be growing in some particular way. If f grows way too much or way too slow, I can't remember which case gives what, but there are some cases where this wouldn't be true if f had a strange behavior. But the condition we put on f is that for all large enough n, there exists a constant so that a times f of n over b is going to be bounded by some constant less than 1 times f of n. And essentially what this is saying is that if we look at the levels that we had earlier, this is saying that f of n is really going to be dominating all the levels. Because if this condition is not satisfied, then it may be that the next levels just keep getting bigger just because f doesn't satisfy this constraint. They get bigger because f is growing in such a way that the a f of n over b that we meet at each level, they just get bigger and bigger. And in that case, we could not say that the dominating part is f of n, as we conclude. But again, this is going to happen pretty much all the time. The polynomials, the exponentials, all the functions we're going to use will satisfy this condition, and so it's very easy to get that. So let me show you some examples. So the first case of the master method is if f of n is upper bounded by a function of the type polynomial n to the L for some constant L which is less than log b of a. Well, in that case, the solution is that t of n is going to be of the type n power log b of a. Now, what this condition means is that f of n is really going to be polynomially smaller than n to the log b of a, because we're requesting that there's a constant L less than log b of a, so that f is in big O of n to the L. So it's not only in big O of n to the log b of a, but it's in big O of something even smaller than that. So let me show you an example. let's say I have t of n is 5 n over 2 plus something in the exact order of n squared. So that means it could come from a recursive algorithm where solving an instance of size n requires solving 5 instances of size n over 2, and then splitting and rebinding them will cost n squared time, roughly. Now, this falls exactly in the case 1 of the master method. Why? Because I'm going to compare the function n power log b of a. B is 2, a is 5. So I'm comparing the function n power log 2 of 5 with the function f of n, which is n squared. Now, this is the case where f of n is in big O of n to the L for some L less than log base 2 of 5. So for instance, if I pick L equal 2, L equal 2 is such that 2 is less than log 2 of 5. Log 2 of 5 is between 2 and 3 somewhere. And so because 2 is less than log 2 of 5, I conclude that I'm in case 1. And then the solution is going to be n to the log b of a, which is going to be n to the log 2 of 5. So again, in this example, it's pretty much as if this part didn't matter very much. Even if it were constant, it would still yield n to the log 2 of 5. Okay, because what really matters is the cost of the recursion. It's where pretty much all the cost comes from. Now, if we understand that this is what's going to happen, that the running time is going to depend on the relation between these constants, a is 5, b is 2, and the function here, which is quadratic. If I want to reduce the running time, if I try to reduce this running time for recombining, but don't manage to change these things, it's not going to make any difference. So if I want to get a better algorithm, I'm wasting my time if I try to optimize this part. It's not really going to change the resolution. If I want to get a better running time, I'm way better looking for an algorithm that doesn't need 5 subinstances of size n over 2. I should either make these subinstances smaller and somehow still get the solution from them, or I should reduce the number of subinstances. Now, this is not simple, okay? But if you're in the business of finding better algorithms, you're way better considering what you can do about A and B than what you can do about the function f of n. Okay, so now let me go on to the second case of the master method, which is the case where f of n is in the exact order of n to the log b of a. Now, I call this the simplified case because the case I first showed you involves some log in it. And this is the case we're going to meet most of the time. The case where f of n and n to the log b of a are essentially of the same magnitude. Well, when that happens, then the solution is going to be of that same magnitude but multiplied by log n. And again, the log n comes in because if you look at this 3 explanation that I gave you, all the levels cost pretty much the same, and there are log n of them, so the total cost is log n times the cost of one level. Now, the more complex situation for case 2 is when f of n is not exactly n to the log b of a, but n to the log b of a multiplied by some log n to some power k. So the case k equals 0 is where there's no log, and this is the simplified case that I just showed you here. Okay? Now, the general case is when there is already a log k of n in the description of, in the description of f of n, because f of n is in the exact order of n log b of a times log k of n. Well, when that happens, well, we just get a solution which is log n times more. So it's the same thing as here, but one more log n in this whole expansion. So it's the same function multiplied by log n, which is just increasing the log k to the log k plus 1. And so let's go through an example of that. If I have a recurrence of the type where to solve an instance of size n, I get 27 subinstances of size n over 3. And the amount of work required for splitting them and recombining them in a solution is of magnitude n cubed log n. Well, when that happens, we are exactly in the conditions of case number 2. F of n is of exact magnitude n to the log b of a, because the log base 3 of 27 is exactly the same as this n cube, because 3 power 3 is 27. And so the function f of n is n cubed log n, and n to the log b of a is n cubed. So we have the same power cube for both of them. So the function n cubed log n becomes n cubed log square n. Okay, so we compare the log base 3 of 27 with n cubed. We find that they're equal, and therefore we're in case number 2. And then the solution is the same function as here, but multiplied by log n. So the solution is n cubed log square n. So basically, to decide which of the 3 cases you apply, it's essentially this line here which matters. It's the line where you compare the exponent in f of n to the log base b of a. And if they're equal, you are in case 2. If one is smaller, the other one is smaller, you're in cases 1 or 3. Okay, so an example of case number 3. In case number 3, we have a situation where f of n dominates over n to the L for some L greater than log b of a. So it really means, again, that f of n is an omega of n to the log b of a, but it's even more than that, because there's a separation between L and log b of a that makes f of n polynomially greater than n to the log b of a. And when that happens, then we get that the cost in the 3 is dominated by f of n, and so the total solution is t of n is in exact magnitude of f of n, and it's as if there was no recursion, basically. But we have to test for this regularity condition, so let me show you on some example. As I said, this is not going to be a problem in general. In general, this regularity condition is going to be satisfied. For instance, for all polynomials, it will be satisfied. And so it's very easy to get to satisfy this condition, but you have to remember doing it, because otherwise the proof doesn't apply. So t of n of this type, so if you have a running time which requires doing 5 subinstances of size n over 2, and you need cubic time to split and recombine the answers, then you compare the log base 2 of 5 coming from a and b and n cubed, which is the time for recombination. Well, in this case, 3 is greater than log base 2 of 5, because log base 2 of 5 is somewhere between 2 and 3. So we're in case 3, because we can put a number between these two exponents. We can put 2.9 is going to be less than 3 and greater than log 2 of 5. And so we have to check the regularity condition. So we have to show that there exists a C such that A of f n over b is bounded by a constant times the function itself, f of n, for some c less than 1. So in this case, 5, 8 is going to solve this condition. So you write down what is A of A times f of n over b. Well, that's 5 times n over 2 cube, which means that if you expand that, you get 5, 8 times n cube, which is bounded by some constant times n cube if you pick c equal 5, 8. And that shows the regularity condition that we were looking for. So you can see that in general, for all polynomials, the same trick is going to work. If I have power 32 here, well, I'm going to get n to the 32 over 2 to the 32, and the same exact proof that I gave here is going to work for any polynomial, essentially. So this is easy to check, but still it's necessary for the proof to apply. And because we are in case 3 and because we satisfy this regularity condition, then we can apply, and the solution is going to be exactly in theta of f of n. And so the solution to this recurrence is in exactly time n cube. And again, it's as if there was no recursion at all. Yes? No, the regularity condition is about the function f. So when you want to show the regularity condition, you want to show that the function f you're using doesn't grow in a completely chaotic way. Because let me show you where this comes from in the earlier picture. So when I showed you this picture, I said that if f of n is much bigger than n power log b of a, I will conclude that the whole sum is going to behave like f of n. But if, as I expand this, and I get a of f of n over b and a square of f of n over b and so on, if those things get bigger and bigger as we go, it's not going to be true that f of n dominates. And if you, I mean, it's possible to find some funky functions f that will fail this criteria, and that as you go down these levels, f, the application of f in all this stuff is going to make the whole thing get bigger and bigger, even despite the fact that f is dominated by, f could be dominating n to the log b of a, but still these levels would count, and this sum would be more than what the case 3 gives us. Okay, so case 3 is where f of n dominates this, but if f doesn't satisfy the regularity condition, then these levels will cost more and more as we go down, despite the fact that f dominates this. So it may be that the most expensive level is going to be somewhere in the middle, and neither the top or the bottom if it doesn't satisfy the regularity condition. So it's really a condition about f in relation to a and b. Okay, so I'm back to case 3. So in such an example, if the power of n dominates n to the log base 2 of 5, then the solution is f of n, which is n cubed in this case. Now, as I said, the master theorem doesn't solve all such recurrences. Okay, so there are situations where it will have the structure of a case 2, but it will not satisfy all the conditions of the case 2. And in that case, we just cannot use it to solve the recurrence. So let me give you an example. If I have a recurrence of this type, T of n is 27 T of n over 3, and the running time for breakdown and recombination is something like n cubed over log n, then I will think that I'm in case 2, because if I compare n to the log 3 of 27, this is going to be n cubed. And so those are going to be equal, and I will think that I'm in case 2. But I'm not, because the function n cubed over log n is not of the type n cubed log k to the n for a positive R0 k. It's actually a negative k. N cubed over log n is n cubed times log n inverse. So it doesn't fit this condition, and therefore case 2 does not apply. And case 1 and 3 cannot apply because these powers are equal. The only case that could apply would be case 2, but the function here doesn't satisfy the rest of the conditions for case 2. And so in this particular example, the master method doesn't tell you the answer. And it's not only that it doesn't satisfy the conditions, but the proof doesn't apply either, and the solution is not what the master method tells us it would be if we tried to apply the master method. It's actually the wrong answer if you try to use the master method. Now, there are many situations where the master method doesn't apply. It's very specific to situations where your input of size n is broken down into sub-instances that are all of the same size. So in this example, they're all of size n over 3, and there's a certain constant number of them. Now, if you change that so that T of n is something in T of n over 2 plus T of n over 5, well, then the master method doesn't apply either. Okay, so if you have a recurrence that uses several different values of smaller n's, if you have something like that, then the master method doesn't apply. It's still possible to solve it, but you have to do it by hand. You have to do it and prove mathematically what the solution to this is. I mean, it's pretty rare that we encounter these things, but there is a very well-known algorithm that has this kind of behavior. It's the problem of finding the median in a set of elements. So if I give you a sequence of n numbers and I want you to find a number which has an equal number of smaller equal or greater equal, then there's a recursive algorithm to find that in linear time that will recurse on instances of size n over 2 as well as instances of size n over 5. Now you're going to say, why n over 5? Well, it turns out that if you're looking for a median, you can choose to break your whole thing in groups of 5. And then manually, in all group of 5, find the median of the 5. So that's a constant time problem. You look at 5 elements and you choose which of them is the median. And then you end up with 1 out of 5. You have a median for all group of 5. And then you look for the median of the medians. And that will give you such type of recursion. So you're going to recurse on groups of 5, and you're going to take linear time, but then you're going to look at the median of the groups of 5, and that's going to take T of n over 5. And this median is going to be a very good approximation of what the median really is. And it's sufficiently close that the rest of the recursion will get you to a linear time solution. It's a pretty fancy algorithm. Even in 251, I don't always cover it, but it's kind of cool to see that there are some recursions of this type that we actually encounter, even with fairly reasonable algorithms. Okay, so all this material, the master theorem, is related to the so-called divide and conquer paradigm. Now, this entire approach is central to very many algorithms. I mean, there are, I would say, easily hundreds of algorithms out there that are constructed in the divide and conquer paradigm. The divide and conquer paradigm is basically what I already told you. It breaks up the input into several subparts. It solves each part recursively, and it combines solution into an overall solution to the entire problem. And the question we ask is, what is the cost of doing these operations? And typically, it gives us a recurrence of the type that we just saw, and that the master theorem can solve. Now, the most common situation we're going to encounter is when it breaks down the input of size n in exactly 2 equal parts of size n over 2. And that was true of merge sort. It's true of many examples, and we're going to see another one, which is binary search. Now, it solves one part in the case of binary search, and it solves both parts in merge sort. And then you recombine them in linear time. So this is probably the most common of these recurrences we're going to encounter, and that's typically what we get for merge sort. This is the recursion we got for merge sort, and it satisfies exactly this situation. And that gives us a very general approach that will give us n log n algorithms in situations where we would naturally go to an n square solution if we did not consider doing things recursively. So sorting is definitely an example of this type. Sorting, if you don't think recursively, almost unavoidably you're going to end up with an n square running time algorithm. And as you introduce recursion and you start thinking recursively as in merge sort, it will also apply to heap sort, to quick sort, and it will also apply to a sorting algorithm you can construct using binary search trees. All of these will have n log n solutions because they're working recursively, and a recurrence of this type will arise from them. So let me show you 2 more examples of this kind of approach. So binary search is a very common thing that we use repeatedly in computer science. So binary search is you're given a set of sorted elements, so you have a sequence A0, A1, up to A of size -1 that are already in increasing order, and you're looking for a particular value V that you'd like to locate in this sequence. Now, of course, if we go sequentially, compare V to A0 and keep going until we find V, well, that's going to take linear time in the worst case, because if you start at A0 and V is the last element, then you're going to look at all the elements before you get there. So binary search is something that you've certainly heard before. It's basically comparing V with the middle element of this array and then continuing with the first half or the second half, depending if V is greater or smaller than the element to which you compared. So this is what a binary search algorithm looks like. It receives an array A, a value V, and bounds low and high that are initialized at 0 and the size of the array -1 at first. So when you invoke this binary search, we will first do that with the entire array. So low and high are going to be the limits of the array. And the purpose of the algorithm is to find where is V in that array if it is. If it's not there, it will return a -1 to indicate, well, it was not part of the array. And if it was, it will return the location where that value was. Now, of course, this can be defined iteratively, but now that we have reached a section where we now understand recursions, let me introduce the solution to this recursively, and it will naturally give rise to a running time of the type of the master method. So the solution here is that we're going to get the low and high value to get closer and closer to each other, and when they actually encounter each other, it will mean that this is where V should be found. So when high and low are equal, then we're going to check if the element in position low of the array is actually V. If that's the case, then we say low is where V is found, and if it's not equal, then we'll say -1, meaning, well, it's not there. Okay, and so all the V's that are given as input and are not part of A will all terminate with the case return -1. It will not say where it might have been. It's nowhere, and so it's just saying -1, meaning it's not in the array. And so this is a termination case of the recursion. It will, the algorithm is going to start with low and high at the extreme limits of the array and recursively call itself on smaller and smaller instances, and ultimately low and high are going to reach each other, and this is when it terminates. So this case, low equal high, is when the recursion terminates, and otherwise we do the second part when low and high are different. Well, actually, high is always going to be greater or equal to low, so when I say different, I actually mean that high is greater than low. And so when that is, I'm going to call the midpoint between low and high. I'm going to make it low plus high over 2. Now, because low and high are integers, that low plus high over 2 could be not an integer, but just consider this division by 2 to be division by 2 as an integer. So mid is sort of the floor of low plus high over 2. It's the largest integer, which is smaller or equal to that value. So this is to figure out in which half should we continue. So we look for the element at position mid. If V is smaller or equal to that element, then we should be looking for V in the positions between low and mid. And this is precisely what we do. If V is smaller or equal to A of mid, we recursively search using the same array, the same V, the same low, but a new upper bound, which is now mid. And otherwise, if V is greater than A of mid, then we compute recursively for the same A, the same V, from position mid plus 1 to high, and so we look for the answer in the highest half of the array. Okay, so this is an example, and this example has some interesting feature that I will explain afterwards. And let's say the value we're looking for is this 5. Then initially, low is going to be the index 0 and high is going to be index 15. And this is the content of the array, which is actually the numbers 0 to 15 in this example. Now, initially, the algorithm is going to search through the entire list from 0 to 15 with low at 0 and high at 15. It's going to compare the element we're looking for with the middle element, which is found at 7 in this case, and it will realize that the element I'm looking for is smaller or equal to 7, so I'm going to change the high from 15 to 7, and the low is going to remain the same, and I'm just going to repeat. I'm going to compare with the middle element, which is 4 in this example, and that element I'm looking for is greater than 4, so I'm going to change low to become 4, and high remains 7, and so again I'm going to compare with the middle element, which is 6 in this case, and I'm going to see that the element I'm looking for is less than 6, and so I move down high to 5. And so finally, I'm going to compare with 4, which is the metal element, and decide to go high. And at that stage, low and high are going to get equal. And it means that the element I was looking for is here in position 5. Now, in this example, we knew that right from the beginning because the elements are always their own index. So this is a very easy situation. If I want to know where is, if value 9 is in the array, I just have to look at position 9 and check that there's a 9 there. But what is interesting with this particular situation is that the high and low selection process is actually selecting the numbers bit by bit. So the first condition, whether the midpoint is smaller or equal to the element I'm looking for, is selecting whether I continue with the numbers starting with a 0 or the numbers starting with a 1. And at each level, this is precisely what I'm doing. At each level, I choose to compare with the middle element, which is basically telling me whether the number I'm looking for has a 0 or a 1 in that position. Now, this description is particular to this situation. It's particular to the situation where the elements of the array are indeed the index at each location, and where the number of elements is a power of 2. So this is a very specific case where you can interpret the evolution of the algorithm as considering and selecting the bits of the value one by one. But the algorithm still makes sense in the general case. So if I go to a situation where the elements are not necessarily the numbers increasing from 0 to n, and where the number of elements is not a power of 2, the binary search still works, and still works for the same reason. It will first consider all the elements and compare with the middle element and choose. So in this example, if I'm looking for the 4th element, it will compare with the middle, decide that it's greater. I'm going to move the lower bound up and keep comparing with the middle element until I get to an interval of size 1, in which case I found what I was looking for. So the recurrence relation corresponding to binary search is that if I have a single element, it will take me one comparison to figure out if it is or not the element that I need. So it will cost me one comparison if n equal 1. But if n is greater than 1, then it will cost me one comparison to decide if I continue with the lower half or the top half. And after that, I'm going to continue searching with half of the elements. So I have one comparison required to choose which half and a time t of n over 2 to figure out in which half is the answer. So this is the recurrence that results from analyzing the recursive solution. And this is a typical example of the master theorem case 2. Log base b of a is 0 because a is 1 and b is 2, so the log base 2 of 1 is 0. And the function f of n is constant, so it's also n power 0. So the two functions are essentially the same. And so the result is that function times log n. Now the function is the constant function, so we don't actually see it. But multiplied by log n, we get that the solution is log n. Okay, so this is a typical example of applying the master method. As soon as you have this recursion, you just need to plug in the a, the b, and the function f, and figure out that this is case number 2, and that the solution is t of n is in big O of log n. All right. I will conclude with this one example for today. I want to tell you how we can use divide and conquer to also do multiplication. So we have seen extensively how to do arithmetic operations such as addition and multiplication as we learned in grade school. And if we do addition, addition takes linear time in the size of the inputs. If I have two inputs of size n, I'm going to take a running time which is proportional to n. And multiplication, as we learned it in grade school, is quadratic time. And for a long time, nobody was able to find any better solutions to that. And the first thing people have done after inventing recursion is try to find a recursive way which is better than the standard or grade school multiplication. So they thought of the following: let's, instead of do it bit by bit in some way, let's do the whole thing recursively. So let's think I have a number n of n digits, and I have another number y of n digits, and let's see how I could recursively multiply them together. Well, the idea to multiply them together is let's consider them as two blocks each. So let's call x to be x0, x1, and let's call y to be y0, y1. And let's multiply recursively. So in order to multiply x by y, we're going to multiply the blocks of x with the blocks of y and reorganize them to give the right answer. Now, what does that mean? Well, think about it in binary. In binary, if I have a number x broken down as x0 and x1, well, it means that the least significant part of x is going to be a number x0 of n over 2 bits. So that's what x0 is. Now, the top part is going to be x1, and its value is 2 to the n times x1, because we want those to fit in the top part of x. And so we multiply by 2 to the n over 2 to put those bits of x1 in the right place. And so in general, the number x is going to be 2 to the n over 2 times x1 plus x0, where x0 and x1 are two numbers between 0 and 2 to the n over 2. So this is a breakdown of x as two pieces, x0 and x1. And I'm going to do the same thing with y. Y is going to be a y0 plus a 2 to the n times y1, which again is just putting the block y1 n over 2 bits further up, so that when we sum them, it gives us y1, y0 like that. Now, if I just formally multiply these two things together, it tells me that the product of x and y, well, is going to be x0, y0 in the lowest part on the right. It's going to be x1, y0 times 2 to the n over 2 here, plus x0, y1 times n over 2 here. And it's going to be x1, y1 times these together, which is going to be 2 to the n times x1, y1. So if I expand this number, it will be made of the following three parts. The rightmost part, which is the product of x0, y0, the leftmost part, which is going to be x1, y1, and the middle part, which is obtained by multiplying x1, y0 and x0, y1, summing them together and shifting them and putting them in the right place. Now, if I do exactly that, what's going to result is that I'm going to need 1, 2, 3, 4 subproducts on smaller numbers. These numbers are going to be all of n over 2 bits. So I'm multiplying numbers half the size, and I'm multiplying 4 of them. And how much time do I need to break down and recombine? Well, I'm going to have to do additions. In particular, I'm going to have to do this addition of 2 numbers that are could be pretty much anything. And I'm going to be adding here, and so all these additions are going to cost me linear time. And I'm going to have a linear time cost for shifting. If I compute x1, y1, then I'm going to have to shift it up n bits to put it in the right place before I add it. So all the extra work, all the work which is not multiplying, will cost me linear time. So that gives me a very natural recurrence inspired by this breakdown recursively. And unfortunately, the log base 2 of 4 is 2, and that 2 is going to dominate the function n, because it's going to give the function n squared. And so this log base 2 of 4 is going to give me a final solution, which is n squared. So this is an interesting approach, but it doesn't give us anything better than grade school multiplication. Now let me jump over this. Okay. Oh no. Here. All right. Here. Okay. Let me give you the bottom line of this discussion. What is really interesting is that this guy, Karatsuba, he realized, okay, the thing is, the middle term here, we're not looking for x1, y0, and we're not looking for x0, y1. What we're really looking for is their sum. And so the way we did it was using 4 multiplications because we were computing these 2 terms separately. Now he noticed, well, we already have x1, y1, and we already have x0, y0. So why try to compute these 2 separately when we only need the sum? So he realized that if you sum x0 with x1 and you sum y0 with y1 and multiply them together, you're going to get x1, y1 plus x0, y0 plus the sum of these 2 terms. So what he realized is that if you first add them and then multiply them, you can then subtract x1, y1 and subtract x0, y0 that you already have, and that's going to give you the sum of the 2 terms. So the sum that you're looking for can be obtained by adding 2 things, multiplying 1 thing, and subtracting 2 things you already have. Now, how much of a difference is this going to make? Well, it means that you're now going to do 3 multiplications recursively instead of doing 4. It's going to cost you more in terms of addition, subtraction, and shift, but this is all linear time anyway. So in terms of the function you're adding here, you're just increasing the constant. You're just spending more time breaking down and recombining, but you're actually doing it with 3 numbers instead of 4. Now, if you plug that in the master method, it tells you that the solution to the recurrence is going to be less than n squared. It's going to be the log base 2 of 3 at the power instead of 2. And this algorithm recursively will multiply in n to the 1.58, roughly speaking. So you can decrease the exponent from 2 to that number just by making it from 3 multiplications recursively instead of 4. And this can be generalized. Again, I'm just going to skip that, but it can be generalized. And you can, by doing it with bigger chunks and breakdown and so on, you can actually do any epsilon greater than 0. You can do multiplication in n power 1 plus epsilon. So if you want to do it in n power 1.01, well, then you can write an algorithm that will do that. It will work for pretty big n's, but it will do it in n power 1.01. So you can be very close to linear. Now, the best known algorithm that we know of today is n log n 2 to the power log star n. Now, what is log star n? It's the number of times you take log until it gets smaller than 1. So it's defined here recursively. Log star of x is 0 if x is less than 1, and it's 1 plus log star of log x otherwise. And that is basically counting how many times you take the log until you get less than 1. Now, this function is growing very, very, very slowly. So this, best known, is like 5 years old. This is a recent result, is very close to n log n. So a lot of people believe that multiplication can be done in n log n and will never be done faster than n log n. But this is what we have right now. All right? See you next week. In the